So it's my honor to introduce the first speaker, Christian Hammer. He's a PhD student at the University of Siegen in Germany. And he is working a lot with laminated glass and quite a lot of other topics. And today he will show you about characterizing interlayers using fiber optic sensors. So Christian, the floor is yours.
Okay, thank you very much for the kind introduction, Christian. Okay. During some tests we made in our lab at the University of Siegen, we have seen that the behavior of laminated glass on the large scale sometimes is different to the materials properties that is determined by small scale tests. And that was the motivation to find some new measurement methods to detect the deformation, the state of stress and the deflection in a comprehensive manner. First of all, I want to introduce you in some topics of research in general. On the left, we have the requirements. Assigned to the requirements are the reduction of mass, the residual load capacity, and the resistance to static as well as dynamic loads, and the manual attack. And from the requirements result the tasks, the developing of interlayers, that is my main research topic, and the reason why I'm standing here and telling you something about measurement systems, and the developing of the interlayers is connected to the high stiffness, to the ductility and the adhesion to glass panes. We have a second topic, the individual layer design, that is designed to several special requirements. And from the task results the challenges. The first one is the localization of critical stress in the glass panes, an applicable material parameter or an applicable materials model, and the prototyping. What happens during a prototyping process and what happens during the manufacturing. And the highlighted box in the middle, developing of interlayers, is important so that we take the characterization of the interlayer material on the top of this chart. The characterization is dealing with the experimental investigation and with the model. The model has to be evaluated and the experiment otherwise. And assigned to the experiment are the statistics, the measurement systems, and focused on the model, the numerical calculation and the analytical calculation. I concentrated on the measurement systems and the numerical model, and that requires a suitable deformation measurement and a suitable FEA model. We have some methods to characterize the materials, especially the polymeric interlayer materials, so I want to sum up. I want to show you some selected methods. On the left we have the standard tensile tests with some measuring dots that you can see on the test specimen below. And we have the dynamic mechanical analysis. And the left one is more to determine the elasticity, the Young's modulus, and the Poisson's ratio. And with them you can calculate the shear modulus. And the right is more for the rheological behavior, such as the temperature and the time dependence. Glass transition point is one of the expressions you all well know. That is shear test. It's a modified shear test. It's similar to the two-rail shear test, and that you can use that you can use too. Okay. And on the right, we have the component scale test. It's the 4-point bending test. And this picture we will see sometimes that we see later in chapter 3. The 4-point bending test sometimes shows some difference between the interlayers. On the left, we have a deflection curve, the bending line, and the state of stress shown below. And the diagram shows the strain on above and below the bottom glass pane. That's the values. The upper values show the tensile strain, and bottom it is the compression strain. So this is well known, and low and high interlayer stiffness show this bending lines, and they can be assigned to a well-known deformation theory like the linear laminate theory, for example. And on the right, we have a different bending line. As you can see, there are turning points, and the state of stress and strain is different to the left. And especially medium interlayers stiffness cause this deformation. And it's not to be assigned clearly to any deformation theory, so the deformation and the evaluation are coupled. An iterative investigation is required. You have to do some loops to evaluate your model. So the determination of the material is done by using FEA, and the detection of the deformation has to be done in a comprehensive manner, not dot by dot, over the entire beam axis. We have some options of strain measurement, which are shown in the picture on the left. This is an example for a digital image correlation, DIC, standard tensile tests. We have some strain gauges as well, and the fiber optic sensing. That's what I want to tell you something more about. So this table shows some selected properties of relevant strain measurement system. We have in the second column the systems. There's photogrammetry or the digital image correlation. We have fiber optic sensing using the Rayleigh signal analysis, and we have the fiber optic sensing using the Bragg signal analysis and strain gauge in the bottom line. And the quantity of measurement points, I call it quantity of measurement points, you have a very high amount of data using the photogrammetry. It's measuring on the area, on the whole surface. With fiber optic sensors using the Rayleigh signal analysis, you're measuring along one line. And the fiber optic sensors using Bragg signal analysis also measuring along one line, but with less data. And strain gauges dot by dot or point. And what we want to measure is the strain in between a composite, and we want to measure the strain on the surface of a composite beam. And we also want to measure in a comprehensive manner, so we have to choose a measurement system that measures in a continuous way, and we have to choose a measurement system that can measure in between. So we have to choose the fiber optic sensing using the Rayleigh signal analysis. And some examples where the fiber optic sensors are applicated in structural engineering. On the left picture we see textile. The next one is from civil engineering, geotechnics, piles and anchors. The fibers are embedded in a concrete anchor that you can monitor it over long-term experiments. And another example given on the right, a rotor blade from a wind power station. It is laminated too. The left graph, bottom left graph shows the progress of strain in a very qualitatively way. And the stress peak or the strain peak shows us very clear the location of a structural defect. So it's a very suitable tool to detect any defects. So the exact location of defects is possible, and the monitoring of structures during manufacturing process as well, and long-term monitoring. So this is application in structural engineering, more to monitor structures or to see what happens during any manufacturing process. But my motivation is to use this method to define values of elasticity, like the Young's modulus or shear modulus. And then we have to switch over to the principles of continuous fiber optic strain measurement. Left picture shows a cross-section of a common fiber that is used in telecommunication. This is elongated, force-induced elongated, or by temperature. And these common fiber, glass fibers that are used in telecommunication applications, they have, caused by the manufacturing process, they have imperfect refractivity, and these imperfectivity cause uneven light scattering along the fiber axis. And that gives an individual frequency pattern of every section of the fiber. So if the fiber is some 100 meters long, so we have in every section, there's an individual frequency pattern. And the frequency shift that is shown in the picture right is related to strain and is also related to temperature. And it's related linear to strain and nonlinear to temperature, but that can be solved by an equation, a polynomial equation. Okay, this setup is developed at our lab. You can see the test specimen that is clamped on the left and stretched on the right by a static load. And the reflectometer, that is the gray box, includes a scanning laser and a detector, and the reference fiber that is between the reflector and the detector. And light comes out from the reflector, goes through the sensor, is backscattered, catched by the detector, and the raw data is comes to the computer, the PC, and a MATLAB routine does the Fourier transformation so that you can process the individual frequency pattern. But it's not the whole pattern shown in this picture, only two positions of the fiber. And we have the black dots are the measuring points. They are of interest on the test specimen, and when the test specimen is elongated, the point moves to the right, and the frequency shift moves too, and it can be related to strain. Well, the frequency shift is related to the strain, and this is done in general with this test setup. Okay, what we have to do next? We have to find out how the fiber can be applied on the glass. And it has to be applied with any adhesive, any glue, and it has to be investigated to identify a suitable adhesive and to determine the relation factor between strain and the frequency shift. And what we wanted to have, we have a measurement system that is conform with strain gauges up to 1,000 micrometers per meter. And we want to look at the behavior during cycling loads. And the results are that a UV hardening acrylate is suitable, the strain is conform up to 1,200 micrometers per meter, and higher strain causes slipping under tensile test. So more than 1,200 micrometers per meter is not very good. Oh, I think I have to hurry up a little because it's only 5 minutes left. Okay. In the next step, you have to investigate the behavior under compression stress, but you cannot take any small test specimen made from glass and give compression load on it, because then you have a buckling problem. So it is suitable to use monolithic glass pane. The test setup is shown bottom right. And what we wanted to find out is the applicability of the adhesive under the compression stress, the behavior during cycling load, and the evaluation of the linear extrapolation of strain from the fiber axis to the glass surface, because there's a little distance between the fiber axis and the glass surface that has to be transferred. So these are the results. The equations bottom left are a simple geometrical, and bottom we see on the left again the test setup with the strain gauges and the fiber that is applicated on the bottom glass pane. We have in between measurement and on the surface of the laminated glass beam. And the results were shown in the graph on the right. The green line shows the tensile stress, and the blue line shows the compression stress. And you see that matches very well to the calculated values that are with a dotted line shown in the picture. And the values from the strain gauge match also very well. So the strain measurement system using an acrylate adhesive is applicable during tensile tests and during bending tests, so that we can switch over to the next step and to evaluate the materials properties from the interlayer in the laminated state. This is the test program for a polyurethane interlayer that is developed by one of our partners. We have done the tensile test and then 2 bending tests. It's 1 bending test but 2 systems. There's a symmetric system, and to evaluate the values that comes from the symmetric system, we have a non-symmetric system. Okay. This picture shows us the application of the fiber. This is applicated on the bottom glass pane, above and below, and some strain gauges as well. And the deformation that we want to reach, it's in the range of 10 millimeters. So you can say that the deformation is in border of geometrical linearity. There's no effects that come from any membrane load-bearing effect. So it is possible to extrapolate values that are measured from the bottom glass pane to the top. And we turned the test setup around and repeated the test, and the values are exactly the same. The picture you've seen in one of the first slides again. On the left we have a strain gauge, a biaxial strain gauge, and we have the fiber going along the entire beam axis. The right shows the test setup with the test engine and some displacement traducers. Well, these are the results of the standard tensile test. You see that there is relaxation behavior, strong relaxation behavior, and on the right you see the Poisson's ratio over the strain. But that is not that important in our case, because the deformation between the glass panes is very small, so that the Poisson's ratio is about 0.48. In the next step, we tested the pure interlayer material in relaxation tests that can be modeled by a simple exponential function with 4 parameters, A, B, C, and D. Where we zoom out the first step, we have the values on the right, and with these values you can also calculate the shear modulus using the cross-section area of the sample of the test specimen. This is detected by the DIC system and also the Poisson's ratio. And what you can see on the slide here are the experimental investigated values from the Fibre. The top picture shows the progress of strain over the beam axis from 0 to 1.1 meter at several time steps. Time step 1 to time step 5. And you can see that the connection between the glass panes decreases with the load steps, and they are increasing with the time. So this is something not new, it's not special, but it shows that it is similar to the tensile test. So we can use values from the tensile test and as well from the DMTA to model the time and the temperature depending. But the elasticity and the values of Young's modulus and shear modulus are different to the component scale, and that is determined by this loop. We start with the shear modulus and the parameters of the exponential function of the regression. We do the FEA calculation, have some results, and if the curve match, the curve from the strain and the curve from the measured strain, it is done, and if it doesn't match, you have to do some loops more by varying the parameters, which are different in sensitivity. So the right chart, I hurry up, the right chart shows the measurement from the small sample, the small scale test. That's the blue line, and the red line is the calculated line that transfer the values on the component scale. And this is done by those test setups. On the left, we have the measurement in green or a dotted line, the first iteration with values from the small scale test, and in the second iteration, it's the blue line. And if we take the values from the blue line and give it to system number 2, the curve matches well. Okay. This table shows the difference, and what you can see is that there is a difference between the small scale test and the component test, but there's nearly no difference between the time dependence. Okay. The results from the tensile test show a lower stiffness. So if you determine values from the component scale, it is, in my opinion, possible to define constructions in a better way. And the calculated stress is a little higher than the measurement. Okay. The pros are that the quantification of the strain is possible. The cons, it is not applicable under high strain rates due to dynamic loads, and the sensors are very fragile. Current work, the investigation of interlayers with higher thickness and stiffness. That's a new research project at our chair. It deals with the development of laminated safety glass with interlayers of higher stiffness and higher thickness, and the investigation of the temperature-induced stress during the manufacturing process, and the measurement system is applicated in this project too. Okay, thank you very much.